we take these readers can be transplanted into other old animals, and these readers trigger lifespan extension. These can be done through the readers. They can be done by adoptive transfer of the DOS T cells. It can be done through the GAPDH depletion of the artificial readers. I think some people have commented on the background controls, the mortality. Yes, there are some background controls dying earlier, roughly 30% to my eye. I think people should focus on the fact on the divergence at the point of the interventions, which is 20 months. At 20 months, there is this diversion. Even if you exclude background mortality, you still have the lifespan extension. In the Sirna control versus Sirna GAPDH, where you do not see this background mortality, you still have this life extension. So I think people should engage with the data, looking at the data for what they are. I anticipate we have other controls that have intact mortality up to 20 months, and there is still the same result. We just wanted to show the data we had at the time. This is preprint. In the final paper, there will be further controls, but the controls, the background mortality before the intervention, have nothing to do with the intervention per se. The individual dogs are not individual animals. This is what PRISM look like, and the animals are what we show in the figure legends of the preprint. We will add more controls, but I wanted to answer this because I have seen, some comments about it, and I was quite surprised about it. So I guess, and I hope this will serve to satisfy them. So our model, telomere regeneration, is quite simple when we strip off of all the noise. We have a T cell and we have an antigen presenting cell. When the T cell engages on fatty acid oxidation, it can cluster through ceramidase activation. It can cluster the CD3 on the bullae of the synapse, and this triggers telomere transfer from the APC. The telomere transfer from the APC proceeds, as we showed in NCB, the greatest sheltering, includes speeds up and so on, through a calcium flux in the APC. These vesicles contain ROT51, and when this lands into the T cell, there's two things that happens. It extends telomeres, ultra short telomeres in the T cell that undergo stem light switch, and upon stem light switch and AD-like division, one of the two daughter cells, CPT18 bright cell, release readers that are depleted of GAPDH because the cell themselves has, somehow reduced the GAPDH tone of the daughter cell, right? So you have the stem-like T cell that within the first division releases these readers. After the subsequent divisions, these capacities are now lost. We have another paper in revision in Nature, so I can't say much about this, but that there are some T cells that are hyperproliferating and that have evolved this unique capacity to produce these readers and to keep us fit. And the overall outcome is systemic rejuvenation, increase of stem-like signaling, and extraordinary life extension. Something also that I think we should train ourselves in thinking is that if you think about the gain we get through telomere transfer, which is roughly 30 times what you get through a telomerase activation, it somehow surprisingly matches incredibly the gain that we have observed in our lifespan extension studies, roughly 20, 30 times more than what in general in the longevity space is observed by turning telomerase or by rapamycin or mTOR inhibition